Moving on to the next part of our discussion on wave motion. Last time, we covered standing wave in a string, a transverse wave. This time, let's have longitudinal wave. Let's take a look at standing wave with sound. Similar to what we did with standing wave in a string, for sound wave, all we need to do is have the sound wave bounce back, and we would have two identical waves moving in opposite direction in the same medium. We would have the condition for standing wave formation. For standing waves with sound, there are two cases to consider, depending on the container that was used. Say we have a fluid medium. The fluid may be contained in a pipe that is open at both ends. We have the open pipe case. Or the fluid may be contained in a pipe that is open at one end and closed at the other end. We have the stopped pipe case. First, let's have the open pipe case. A fluid medium contained in a pipe that is open at both ends. For the open pipe case, the harmonics is given by Fn is equal to V over lambda n. Lambda n is still equal to 2L over n, just like in wave in a string standing wave. Fn is equal to Nv over 2L. V is speed of sound in a fluid medium. We know the equation for speed of sound in a fluid medium. V is equal to square root of bulk modulus over volume density. Thus, Fn is equal to N over 2L square root of bulk modulus over volume density. And Nv over 2L may be written down as Nf1. N is still the harmonic number of segments. N is still whole numbers or integers greater than 0. We have N is equal to 1, 2, 3, 4, 5, and so on. L is the length of the container, length of the pipe, length of the open pipe. And again, B is bulk modulus of the fluid medium, and rho is the volume density of the fluid medium. N is equal to 1, 2, 3, 4, and so on, number of segments. Just like with the harmonic number of standing wave in a string, thus, we have a similar naming convention for the harmonic frequencies for the open pipe case. F1 is equal to first harmonic frequency or fundamental frequency. F2 is second harmonic frequency or first overtone. F3 is third harmonic frequency or second overtone, and so on. On the other hand, for the stopped pipe case, a fluid medium contained in a pipe that's open at one end and closed at the other end, the harmonics is given by Fn is equal to V over lambda n. This time, the wavelength lambda n is given by 4L over n, such that Fn is equal to Nv over 4L. L is the length of the stopped pipe, and V is speed of sound in fluid, so it's still equal to square root of bulk modulus over volume density. Thus, Fn is equal to n over 4L times square root of bulk modulus divided by volume density. And NV over 4L may be written down as NF1. N is still the harmonic number, but this time, instead of being the number of segments that is formed in the medium, N is number of half segments, and N is a series of odd numbers. N is equal to 1, 3, 5, 7, 9, and so on. Add integers greater than 0. So N is a series of odd numbers. We have what is referred to as odd harmonics. For odd harmonics, the naming convention for the harmonic frequencies is slightly different. So please take note of this. For odd harmonics, we have F1 is the first harmonic frequency or fundamental frequency. The next frequency after F1 is F3. F3 is the third harmonic frequency. It's the first overtone. And then we have F5, fifth harmonic frequency or second overtone. F7 is the seventh harmonic frequency or third overtone. F9 is the ninth harmonic frequency, fourth overtone, and so on. Now, sound can also travel through solids. Thus, we also have the open pipe case and stopped pipe case for a solid medium. And the equations are pretty much the same as the open pipe case and stopped pipe case for the fluid medium. Just replace the bulk modulus by Young's modulus. Thus, for the open pipe case, we have Fn is equal to V over 2L square root of Young's modulus over volume density. While for the stopped pipe case, we have Fn is equal to V over 4L square root of Young's modulus divided by volume density. And that's it for now. That's it for our discussion on standing wave with sound. We'll continue our discussion in the next video. In the next video, we'll take a look at a few examples. So again, that's it for now. Thank you for watching.